is QMG bringing you more information from the exciting world of quantum mechanics. Today, I have the pleasure of presenting a wonderful experiment that was carried out by a group of scientists, obviously. And here is the name of the title of the paper. This came out a few days ago. Scientists discover a way to make quantum states last 10,000 times longer. This is big. This is big. It is important in quantum mechanics to be able to make sure those quantum mechanical systems remain pure in order to be able to perform operations that are useful to compute information or to carry out processes that would allow to maintain the secrecy of information whenever there is transmission of information by means of a quantum internet, for example, right? So we're going to see how they achieve this wonderful achievement, and it is very ironic in the way in which they actually solve this problem, and it makes you think about where these might be relevant as well, not just in the realm of quantum computing, of course, but there might be other situations where something like this might be very useful. I will tell you about it. Let's read here. A team of scientists at the University of Chicago's Pritzker School of Molecular Engineering announced the discovery of a simple modification that allows quantum systems to stay operational or coherent 10,000 times longer than usual, of course. Let me see if I can scroll this one up. I guess he got stuck. So now that it seems very amazing when you read that number, but really still it's a very short amount of time. What is important about this paper is that they actually achieve that process by adding noise to the system. Let me explain. When you have a pure quantum system, you want to isolate it, okay, from the rest of the world, temperature, electromagnetic fields, you name it, because that can break the quantum system. Quantum computers, for instance, have to be at very low temperatures in order to avoid temperature, to have an effect on the quantum system. So how did they achieve that? Okay, did they freeze it even more below to the point that it just doesn't move at all in any way? Actually, no. Okay, they achieve that in a very clever way. Okay, let's keep reading. If we can harness it, quantum technology promises fantastic new possibilities. But first, scientists need to coax quantum systems to stay yoked for longer than a few millionth of a second, of course. Let's see. All right. A team of scientists at the University of Chicago's Pritzker School of Molecular Engineering announced the discovery of a simple modification that allows quantum systems to stay operational or coherent 10,000 times longer than before, though the scientists tested their technique on a particular class of quantum systems called solid-state qubits. They think it should be applicable to many other kinds of quantum systems and could thus revolutionize quantum communication, computing, and sensing, right? So it doesn't state it in this paper, but if you read the actual paper, they actually carry out the experiment on the spin of particles, right? So the spin, you can imagine, the particles are doing what they say, spinning around. So in spin one half, you can have, you can have it in one direction or the opposite, right? Up or down. That's how I usually represent it. And so they basically manipulated the spin of the particles with an external with an external electromagnetic field. And let's keep reading here. Okay, the study was published August 13 in Science, so it's very recent. Okay, it's a breakthrough. This breakthrough lays the groundwork for exciting new avenues of research in quantum science, said study lead author David Shalom, the Liu family professor in molecular engineering, senior scientist at Argonne National Laboratory, and director of the Chicago Quantum Exchange. The broad the broad applicability of these discovery, coupled with a remarkably simple implementation, allows these robust coherence to impact many aspects of quantum engineering. It enables new research opportunities previously thought impractical. Right. I can think of one place where these would be very helpful, and that's in quantum money. If you watch my video on quantum money, which is not something that I came up with, something that is published. If you look at my video, you can see that in quantum money, you need a system that remains coherent for a long time, right? Because if you're going to use a system of quantums as money, you better make sure they don't dissolve right away, right? If you want to keep them in the vault, you got to make sure they stay there indefinitely, right? And so we're not there. I can tell you if they could achieve coherence for a very long time, then we would be talking about quantum money, something that you don't hear very much in the conversations on quantum on applications of quantum mechanics, because quantum money right now is very impractical for that reason, right? Because we cannot maintain coherence of those systems for a long time. On the other hand, for quantum computing, as long as you have enough time before they dissolve, it's fine, right? Let's go to the next one. Down at the level of atoms, the world operates according to the rules of quantum mechanics, very different from what we see around us in our daily lives. These different rules could translate into technology like virtually unhackable networks or extremely powerful computers. The US Department of Energy released a blueprint for the future quantum internet in an event at UCU Chicago on July 23, but fundamental engineering challenges remain. Quantum states need an extremely quiet, stable space to operate, as they are easily disturbed by background noise coming from vibrations, temperature changes, or stray electromagnetic fields. It's interesting that in this paper, they're not talking about quantum money. They're talking more about the communication aspects of quantum mechanics. But it is true, right? For some processes, you must maintain the entanglement long enough, right? If you watch one of my videos on cryptography, quantum cryptography, where I talk about the quantum internet, I mention it. You can actually see that you need an entanglement. I made an entanglement with 3 particles, and you have to maintain that long enough in order for that particular scheme to work. So definitely having longer time of coherence is a useful thing. On the other hand, you can do certain processes fast enough, okay? Not all processes need a lot of time. Not all processes need those quantums to remain coherent for a long time, because there are some useful quantum mechanical operations that you can do right away, right? Thus, scientists try to find ways to keep the system coherent as long as possible. One common approach is physically isolating the system from the noisy surroundings, but these can be unwieldy and complex. Another technique involves making all of the materials as pure as possible, which can be costly. the scientists at U Chicago took a different track. Of course, they tried the obvious things. They thought about the obvious things, right? Like, um, I guess, like I was joking at the beginning, make it more cool, lower the temperature, right? You just can, you can only can do it up to a certain limit, right? And the other one, which I didn't think about, is making all of the materials as pure as possible, right? Okay, so what did they do? Here comes their genius. Okay, you gotta look at this. With this approach, we don't try to eliminate noise in the surroundings. Instead, we trick the system into thinking it doesn't experience the noise, said postdoctoral research Kevin Meow, the first author of the paper. And this is the key, right? They are adding noise in order to deal with the problem of um, of the system not remaining pure, right? So you might say, well, how does that work, right? Adding disturbance, well, not noise, disturbance to the system, and somehow that helps to maintain the system coherent. What's going on here? Let's keep reading. This is very interesting, right? In tandem with the usual electromagnetic pulses used to control quantum systems, the team applied an additional continuous alternating magnetic field. By precisely tuning this field, the scientists could rapidly rotate the electron spin around the system to tune out the rest of the noise, right? So when you're dealing with spins, I mean, when the system is not coherent, right, you don't expect to have the spins uh, in in any in any way in which you can say their measurements are correlated, right, for a long time, right? So by adding noise to the system, okay, and specifically a microwave, they were able to achieve coherency in the system. Okay, let me keep reading, and I will make a little comment here. To get a sense of the principle, it is like sitting on a merry-go-round with people yelling all around you. Meow explained. When the ride is still, you can hear them perfectly, but if you are rapidly spinning, the noise blurs into background. Okay, it's a very nice analogy, right? Because it kind of shows you how noise, okay, can become irrelevant when you start changing the situation in such a way that that noise doesn't act in a in the loses its effectiveness, right? And from a thermodynamical perspective, this is very interesting, right? Okay, because when you have a pure quantum system, basically you have very low entropy, right? So you might be saying, well, wait, how does that work, right? You're adding, pumping some energy into the system, and somehow you achieve lower entropy. So how does that work? Well, you know what, the best from a thermodynamical point of view, you can think of, here's an analogy, global warming, for instance. Okay, if you heat up the Earth by pumping extra energy into it, what happens? It heats up overall, but the weather becomes more extreme, right? So some areas get hot, of course, and overall there's an increase in heat, but there are areas, where there is a where there is cold weather that can become more extreme, right? So that's a good way to think uh, about the situation, to make sense out of the thermodynamics of the situation, right? Because it seems paradoxical, right, that you're adding, pumping an electromagnetic pulse into the system, and somehow you end up bringing up coherence into the system, right? Let's keep reading here. This small change allows the system to stay coherent up to 22 milliseconds, 4 orders of magnitude higher than without the modification, and far longer than any previously reported electron spin system. For comparison, a blink of an eye takes about 350 milliseconds. Okay. The system is able to almost completely tune out some forms of temperature fluctuations, physical vibrations, and electromagnetic noise, all of which usually destroy quantum coherence. Now, here's something to think about. Okay. Okay, how come that many systems in biology do not work by means of a complicated quantum mechanical process, right? It is possible, right? But why usually we think that it is irrelevant? Well, because there is a lot of noise in biological systems, right? There's some of those factors: physical vibrations, electromagnetic noise, okay, temperature fluctuations, which can make any quantum system become decoherent, right? But just some food for thought: could it be? Could it be that in some biological systems, sometimes, very rarely, but it does happen, you have enough coherence for those quantum systems to do something that is significant for the correct functioning of some biological process? Who knows, right? Who knows? But that comes to mind, when you read something like this, if you want to apply it and think outside the box, right? Just some food for thought, right? Let's keep reading. This approach creates a pathway to scalability, said Auskalom. It should make storing quantum information in electron spins practical. Extended storage times will enable more complex operations in quantum computers and allow quantum information transmitted from spin-based devices to travel longer distances in network, right? So if you have a process that involves entanglement with spin, then this might be very helpful, right? Though their tests were run in a solid-state quantum system using silicon carbide, the scientists believe the technique should have similar effects in other types of quantum systems, such as superconducting quantum bits and molecular quantum systems. This level of versatility is useful for such an engineering breakthrough. All right. There are a lot of candidates for quantum technology that were pushed aside because they couldn't maintain quantum coherence for long periods of time. Meow said, "These could be reevaluated now that we have this way to massively improve coherence." Well, not good enough, in my opinion, for quantum money, right? Because that would really change the way in which we deal with economic transactions, right? And it would be safe, right, if we had quantum money, because only the bank or in some trusted people could get the information from the money to verify it, but they wouldn't be able to copy, which would be very helpful, right? See, the best part is it's incredibly easy to do. Absolutely, I agree with them. He added, the science behind it is intricate, but the logistics of adding an alternating magnetic field are very straightforward. And that is true, right? If you read the paper, it's just a small paper. When I look at the actual paper, I was flipping it and saying, where's the rest? That's it. Very simple paper. The math is easy, okay? If you're scared of math, this is the easiest paper that you ever read, Okay, very basic stuff, really. Okay, you should check out their paper. All right. Okay. Well, in fact, there is a paper right there. Okay. Well, it was fun being with you. Okay, I will see you next time. And for those about to quantum, we salute you.